Okay, now let's look at the non-visual senses. We'll start off with hearing. First, sound waves. Sound waves are the environmental stimulus that is going to be required for us to be able to hear something. From the environment, they pick up the sound waves and then get them to the brain. Sound waves are compressed and expand air molecules, and the ears are designed to detect these brief pressure changes. So audition is the sense or act of hearing. The amplitude again is the height of a wave. It determines the intensity or loudness of sound waves. We have length or frequency determines the pitch. Frequency is the number of complete wavelengths that pass a point in a given time, for example, per second. And pitch is a tone's experienced highness or lowness, depends on the frequency. And sound is measured in decibels. So 0 decibels is the absolute threshold, not the absence of sound, just less than humans can hear. 60 decibels is what you have in normal conversation, and 85 plus decibels are prolonged exposure can cause hearing loss. We saw this particular slide a little bit previously in the other section on visual senses. Here we have similar types of ideas. We have a short wavelength that is high frequency, high pitched sounds. The long wavelength or low frequency for low pitched sounds. Great amplitude, loud sounds. Small amplitude, soft sounds. So these waves and how they look can determine quite a bit as to the quality of what we're actually hearing. Either something that's high pitched, low pitched, loud, or soft sounds. So sound waves are bands of compressed and expanded air. Human ears detect these changes in air pressure and transform them into neural impulses which the brain can decode as sound. Sound waves vary in amplitude, which is perceived as differing loudness, and in frequency, which is experienced as different pitch. So we have vibrating air is sound waves. They enter the outer ear and pass through the auditory canal to the eardrum. The middle ear is a chamber between the eardrum and the cochlea, which contains three tiny bones that amplify the vibrations of the eardrum. The cochlea is sort of a coiled, bony, fluid-filled tube in the inner ear that contains the nerve receptors. The inner ear, the innermost part of the ear, contains the cochlea, semicircular canals, and the vestibular sacs. Sound waves strike the eardrum, causing it to vibrate. The tiny bones in the middle ear pick up the vibrations and transmit them to the cochlea, this coiled fluid-filled tube in the inner ear. It ripples in the fluid of the cochlea, bending the hair cells lining the surface, which triggers the impulse in the nerve cells. Axons from these nerve cells transmit a signal to the auditory cortex. So here we see an example of it. How we transform sound waves into nerve impulses that our brain can interpret. The outer ear funnels the sound waves to the eardrum. The bones of the middle ear amplify and relay the eardrum's vibrations through the oval window and the fluid-filled cochlea. As shown in this detail of the middle ear and the inner ear, the resulting pressure changes in the cochlea fluid-filled chamber, the basilar membranes to ripple, bending the hair cells on its surface. The hair cell movements trigger the impulses at the base of the nerve cells, whose fibers converge to form the auditory nerve. That nerve sends neural messages to the thalamus and then send it on to the auditory cortex, where we then know what we're hearing. Now, sometimes issues can occur when it comes to our ability to hear. We have sensorineural hearing loss or nerve deafness, damage to cell receptors associated nerves. This is a more problematic type of hearing loss. The cells themselves may be damaged. The hair cells may break, meaning that whatever that hair cell was there to detect that frequency of sound, it may have lost that capability. We also have conduction hearing loss, damage to the mechanical system that conducts sound waves to the cochlea. Recently, we've seen things like cochlear implants, a device for converting sounds into electrical signals and stimulating the auditory nerve that electrodes threaded into the cochlea. So, perceiving loudness, pitch, and location. Responding to loud and soft sounds, the brain interprets loudness based on the number of activated receptors. Soft tones activate fewer hair cells. Loud, hard tones, more hair cells are going to be activated. People who lose all hearing in one ear often have difficulty locating sounds. Obviously, one of the key things, as we saw with binocular cues for vision, well, we have two ears, and these ears sometimes can help us locate the source of sounds in our environment. Hearing different pitches. Place theory in hearing. This theory that links the pitch heard with the place where the cochlear membrane is stimulated. It best explains our ability to hear high pitches. Frequency theory or temporal theory in hearing. Here, the rate of nerve impulses traveling up the auditory nerve matches the frequency of a tone, thus enabling its pitch to be sensed, and this explains low pitches. And some combination of the place and frequency theories seems to explain the pitches and the intermediate range. So basically what it comes down to is that we have several theories to help us explain how it is that we're able to hear certain types of pitches, where they fall in certain ranges. Place theory for one group, frequency theory for another, and then some combination for the remainder. So as I was saying earlier, we locate sounds, and locating sound does have a major survival function. If we feel like we're in danger or risk of something and we hear something, we want to know and be able to figure out where it's coming from. So the sound waves strike one ear sooner and more intensely than another. That gives us a clue as to where the source of the sound is coming from. From this information, our brain can compute the sound's location. The other senses that I want to touch on real quickly, touch. Sense of touch is actually a mix of four distinct skin senses: pressure, warmth, cold, pain. Other skin sensations are variations of these basic four. So we only can experience directly pressure, warmth, cold, or pain, and the different combinations of these will allow us to perceive different types of sensations. Let me give you an example that you may be familiar with. Sometimes when you're touching some sort of a doorknob, for example, like that's cold. When you have cold and a sense of pressure hit your hand or skin in the right way, you will perceive a sensation of wetness. So pressure, cold, wetness. So again, all the various types of things that we can experience, they're a combination of one or a combination of these four things: pressure, warmth, cold, or pain. Now, when it comes to pain, pain is your friend. And what do I mean by that? Pain tells us when there is something wrong. It's a warning sign to the body. Without being able to experience pain, the organism could get themselves in some life-threatening situations. So, pain. Women are more sensitive to pain than men. Pain sensitivity depends on genes, physiology, experience, attention, and your culture. For example, sometimes you may be in pain, but if you get distracted, your attention goes elsewhere, you may not experience the pain in the same way. We also know the culture. Some cultures have sort of a stiff upper lip about pain, that you don't show people that you're in discomfort or having some sort of pain issue. They may experience pain psychologically somewhat different than other people from other cultures who may have a different perspective of pain. The gate control theory. The spinal cord contains a neurological gate that either blocks pain signals or allows them to pass to the brain. The gate is opened by the activity of pain signals traveling up the nerve fibers. It is closed by activity in the larger fibers or by information coming from the brain. So when it comes to our experiencing of pain, we know that like we've seen numerous times already, there is a biopsychosocial factor in explaining our personal experience of pain. So biologically, activity in the spinal cord, large and small fibers, genetic differences in endorphin production, the brain's interpretation of the central nervous system activities, all will have a great deal of influence on what we experience personally when it comes to pain. Psychological influences: are we paying attention to the pain? Learning based on our experience, and also expectations of whether or not we're supposed to feel pain. Is it only a small pain or a big pain? And we have social cultural influences, the presence of others. So if we hurt ourselves and there are other people around, you may not feel the pain as much. You're not going to start wailing and crying in front of your friends. So the presence of others may influence our experiencing of the pain. Empathy of others' pains and cultural expectations all play a role as well. So sensory receptors, we have the nociceptors, respond to potentially damaging stimuli by sending an impulse to the spinal cord, which passes the message to the brain, which interprets the signal as pain. Now sometimes, under certain situations which we've discussed before, when we experience certain types of pain, we may automatically respond to it well before we get any instructions from the brain to do anything about it. So we are sort of pre-programmed in a sense to respond to certain types of things automatically without having to wait for instructions. It saves damage to the organism, or ourselves in this case, so we can respond to things immediately as opposed to having to wait for it. Now, when it comes to controlling pain, we know that a placebo, which we talked about previously as well, reduces the central nervous system's attention and responses to pain. So somebody can be given a placebo, which again does not have any active ingredient whatsoever, and they will feel better. So again, their expectation of the pain dissipating can actually make it happen. Distraction. It draws attention away from painful stimulation. When they've conducted functional MRI scans, reveal virtual reality play reduces the brain's pain-related activity. So the idea is sometimes when somebody's having a pain in one part of their body, they may rub their belly or something of that nature to distract them, to draw attention away from the painful stimulus. That can work as well. We also see hypnosis. This is sort of a social influence theory, or disassociation. Disassociation, dual processing. Sensory information does not reach the areas where pain-related information is being processed. So the idea is, if you are going to the dentist and they have an option of this particular dentist to put you under hypnosis as opposed to giving you some drugs, of course, myself, I'll take the drugs. But if someone were inclined to do that, they could be put under hypnosis, a heightened state of suggestibility, and told or guided to not feel the pain. And the idea behind this is that the information of the stimulus that you're receiving is not going to the pain-related information centers where it can be processed. Therefore, you don't feel and you don't experience the pain when that procedure is going on. So also part of this could be an explanation of selective attention, that they are making you focus on something else and not that your tooth is getting drilled into. So this is part of the post-hypnotic suggestion that you will not feel the pain, it will not be a discomfort, you know it's there. So there are a variety of ways in which pain can be controlled. Some of the other senses. One other sense is that of taste. Like touch, taste involves several basic sensations. They can be influenced by our learning expectations as well as perceptual biases, and it does have a survival function. We know, for example, we have the taste of sweet, salty, sour, bitter, or savory or umami. So the idea is that these things have certain things that they tend to be associated with. Sweet with energy source. Salty, sodium essential to physiological processing. Sour, that's potentially a toxic acid. Bitter, potential poisons. So these things aid in our survival. And so when we tasted something, our ancestors long ago, they see this unusual berry, they taste the berry, and if it's bitter, that may warn them to stay away from that food, that berry, because it could be potentially poisonous. So these things, they're there, and we make wonderful meals based on all this type, the taste and whatnot, but they have other functions as well. So taste. Inside each little bump on the top and sides of our tongue are more than 200 taste buds. Each bud contains a pore with about 50 to 100 taste receptors. Each kind of receptor reacts to different types of food molecules and sends messages to the brain. Oh, real quickly, let me go back. So when it comes to taste, you may have noticed this with your parents or your grandparents, that they put a lot more salt on food or more hot sauce or what have you. The reason for that is as you get older, your sense of taste will start to decline. So you'll have to season the food a little bit more to get the type of sensation that you want when it comes to how you want your food to taste. When we're rather young, we have our heightened taste buds where we can taste the best. When it comes to our food, to be able to taste the food. But as we get older, we do not have those same degree of taste buds that we used to. Also, we see too, when it comes to taste, taste will have a lot to do with the culture as to what types of food one eats. We've seen that before as well, and we'll see that in a future chapter as well. So the notion is we have these receptors, and because we eat at least 3 times a day, if not more, there's a lot of physical contact with these receptors. Therefore, these receptors, more so than most, are going to be changed out on a more regular basis because they go through a lot of hard work having to be physically in contact with the food and things of that nature. Now, it should be noted that in order for us to taste something, the food must be in a solution, a liquid solution. That is why when we see a plate of food, we begin to salivate, because in order for us to taste the food, it must be suspended in the liquid, our saliva in this case, for us to be able to taste the food. All right, now let's get to smell. Experience of smell. It's olfaction. That's what we call the experience of smell, olfaction. Like taste, it is a chemical sense. The olfactory receptor cells are located in the olfactory bulb in the nose. A combination of several odor molecules stimulate different receptors to detect them. These patterns are interpreted by the olfactory cortex. So we see the young girl in this image here is sniffing a flower, a rose it looks like, and odor molecules from the rose flows up into the nasal cavity and then lands on the olfactory membrane where there are receptor cells. Then the information is going to be transmitted through the receptors to the olfactory nerve, so it can be sent to the olfactory brain area where it can be processed and we know what it is that we're smelling. Now the key point here for our sense of smell, we must take in the molecules of whatever it is that we are smelling. So it's a chemical process. When we're out and about walking around the yard and we smell something that's really bad, okay, that means whatever that smell, whatever the source of that smell is, molecules from that substance has flowed up your nose so that this process can begin, so that we can actually smell it. And of course, that can give us a lot of information as to what it may be, when it gets processed by our brain. But that is the process. The molecules must get into the organism for us to be able to smell it. So the nose knows. Humans have some 20 million olfactory receptors. That's a lot. But compared to a bloodhound, we're not in the same league. A bloodhound has 220 million. So this is why the world may be different for a human versus a dog. And this is why the dogs are always sniffing everything, because they have so many more olfactory receptors than we do. They can detect a lot more than we can. They can smell things that we couldn't even imagine to be able to smell. So when you have a dog and their noses to the ground and they're following some weird circuitous path, they are probably following a trail and they're actually smelling something that we have no ability to smell whatsoever. So when it comes to smell, we need to also understand about taste to a degree as well. So information from the taste buds travel to an area between the frontal and temporal lobes of the brain. It registers in an area not far from where the brain receives information from our sense of smell, which also interacts with our taste. So, point. When you taste food, part of this thing that you are tasting has nothing to do with taste. It's also going to involve your sense of smell. If you've ever had a cold, and let's say you still have a little bit of the cold symptoms, and someone gives you your favorite dish, let's say it's lasagna, but when you taste it, it tastes off. It tastes off because your sense of smell is off kilter. And what we don't realize sometimes is that when we experience taste, it's not just taste alone, it's taste plus smell. So smell is a very important component to our ability to taste. So if, for example, we get an apple and a potato and we cut them up into cubes, so we have a cube of apple and a cube of potato with a toothpick in it, and we block your nose with a clothespin and then tell you to taste the apple and the potato and tell me which one is different, you may be hard pressed to be able to detect the difference, because they both have similar textures, but because your nose is being blocked up, you have no sense of smell. Therefore, you cannot determine which one is which is the potato and which is the apple. Now, the brain circuitry for smell also connects with areas involved in memory storage, chapter we'll get to a little bit later. So memory storage, which helps explain why smell can trigger a memory. So we'll talk more about that a little bit later, but the idea is that smell is very much related to memory based on the route that it takes throughout our body, that it goes next to one of our memory storage facilities, so to speak. Therefore, when we smell a certain thing, it can trigger a memory that we've associated with that particular smell. The other senses are body position and movement. Kinesthesia, the system for sensing the position and movement of individual body parts, which also interacts with vision. We have vestibular sense, the sense of body movement and position, including the sense of balance. All these are very important, particularly if you're doing athletics or something that's very, very physical. We need to know what our body is doing. We need to know where our feet are when we're running really fast. So there are certain types of systems in place that allow us to be able to detect our body orientation, how we're moving, whether or not we're balanced or not, and these things are very important to our survival and functioning. So summarizing some of our senses here, we have vision, where we have light waves striking the eye, the receptors of the rods and cones. Hearing, sound waves striking the outer ear. Inside we have the cochlear, we have hair cells in the inner ear. Touch, pressure, warmth, cold on the skin. Skin receptors detect these types of things, and the combination of them gives us different types of sensations. Taste, chemical molecules in the mouth. Basic tongue receptors are sweet and sour and so on. Smell, chemical molecules breathe in through the nose. Position and body movement with kinesthesis, any change in position of the body part interacting with vision. Kinesthetic sensors in the joints and tendons tell us where our arms and legs are and what they're doing. Position, movement of the head, the vestibular sense, very important, movement of fluids in the inner ear cause the head and body move. So we know whether or not we're balanced or not. Sometimes when you have a really bad cold or flu symptoms, the vestibular sense may be a little bit off. That's why we can get very dizzy at times and can cause quite a bit of problems. All right, so again, we talk about sensory interaction. Senses are not totally separate information channels. Sensory interaction, the principle that one sense may influence another, as when the smell of food influences taste, smell plus texture plus taste equals flavor, and so on. Embodied cognition, influence of bodily sensations, gestures, and other states on cognitive preferences and judgments. Physical warmth may promote social warmth. Social exclusion can literally feel cold. Political expressions may mimic body positions. So what it comes down to is that sensory interactions, we display a lot when it comes to and sense a lot when it comes to physical warmth, social warmth, social exclusion, feeling cold. So we may use these to describe our feelings and our thoughts quite often. And sometimes you also know people who use their hands quite a bit to communicate. So embodied cognition talks about how our body sensations and gestures and other states may demonstrate cognitive preferences and judgments. And finally, a couple of things I wanted to touch base on real quickly, which were hinted at in this particular chapter, extrasensory perception. So we talk about senses, and we talk about the normal senses that we talk about, but what about extrasensory perception? It can be defined literally as perception without sensation. So we have perception, but there is nothing there for us to be sensing. So believers in ESP think that it involves getting accurate information directly to the mind, skipping the known senses. Types of ESP include such things as telepathy, clairvoyance, and precognition. The evidence for ESP is all anecdotal and very controversial. People seem to notice times when predictions come true and perceptions match reality, but tend to disregard those times when they do not. And finally, perception without sensation. Most relevant ESP claims are telepathy, clairvoyance, precognition. ESP is studied by parapsychologists. Okay, now they've done some research. BIM and 9 experiences seem to suggest that participants could anticipate future events. Critics, however, are many. Critics said there were methodologies that were flawed. Analysis was viewed as flawed as well. Most research by psychologists who are legitimate psychologists and scientists are very skeptical of any type of thing when it comes to ESP. Now, granted, one of the main issues would be is that things that we cannot objectively assess, very hard to look at and examine scientifically. All right, that's it for that.